Okay, so we've done estimating a population proportion in 8.2. And so now we're going to estimate a population mean. So go ahead and start thinking about what are the things that we did in 8.2 that are going to be the same, and what are the things we're going to have to adjust that are going to be different. And then I've got to add just a couple more things to that. And otherwise, 8.3 follows exactly like 8.2. Okay. In this section, we will be estimating the population mean. But if we don't know the population mean, then we don't know the population standard deviation either. So how do we estimate mu when sigma is unknown? Our best guess for the value of sigma is the sample standard deviation S sub x. So if we don't know mu, we don't know sigma. But if we don't know sigma, then the next best thing is S sub x, the standard deviation from the sample. So when we do this statistic plus or minus the critical value times the standard deviation of the statistic, that's my confidence interval. My statistic is going to be x bar plus or minus my critical value, z star, standard deviation of statistic. Well, there's the standard deviation of statistic. However, if I don't know sigma, I'm going to replace him with S sub x. Okay, so that makes sense. So when you write it, you're not going to write sigma, you're going to write S sub x. Okay. Actually, when you're finding a confidence interval for a population mean, you're not going to use a true normal distribution z-score. You're going to use a different distribution that's very similar to normal. It's called a t-distribution, not capitalized T. All right, now I know on your copy it's a little harder to read, so look at mine. It says t-distributions have more area in the tails than the standard normal distribution. So let's talk about, all right, the standard normal distribution is the solid line. So that's this. So that's the standard normal distribution. The tails are thin. It goes all the way almost to the x-axis, but not exactly. Now, the other two lines are both t-distribution. They have different, what's called degrees of freedom. The more chunky dotted line, that's this one right here, has 2 degrees of freedom, and the thinner one, the lighter one, has 9 degrees of freedom. So what we can say is that as the degrees of freedom increase, the graph approaches more of a normal shape. The smaller the degrees of freedom, the thicker the tails are. And when I say thicker tails, I mean it's got more area out here under the tails. And that's going to bring the top peak down a little bit because it's got to compensate for the area under the tails. So it definitely has more area under the tail. So when you draw a t-distribution in your problems, instead of drawing a normal distribution, you're going to draw and show them that it has thicker tails. Okay, you're not going to draw those lines. But when you draw it, you're going to draw it and show that you know it's a t-distribution and not a normal distribution. Let's see, to find a t, just like to find a z. So to find a t, so z comes from a normal distribution, a t comes from a t distribution. I've got my sample statistic, my parameter, and my standard deviation of my statistic. Notice that I have I have S sub x instead of sigma because I don't know mu. Degrees of freedom, you're going to write as DF, and degrees of freedom is N minus 1. It's always 1 less than the sample size. So if your sample size is 30, you're going to write degrees of freedom equals N minus 1, 30 minus 1, 29. Okay. The density curve of the t-distribution are similar in shape to the standard normal curve. They are symmetric, about 0, single-peaked, and bell-shaped. The spread of the t-distribution is a bit greater than that of a normal distribution. So it has more variability, it has more probability in the tails, and less in the center. Now, here's why. Remember, for a t-distribution, you don't know sigma. So you are substituting the estimate S sub x for the fixed parameter sigma, and that gives you more variation into your statistic. So the t-distribution just allows for that. As the degrees of freedom increase, the t-density curve approaches the standard normal curve more closely. This happens because S sub x estimates sigma more accurately as the sample size increases. So as your sample size increases, it gets less variable, and S sub x approaches what the true sigma would be, and it looks a little bit more normal. So in using S sub x in place of sigma causes a little extra variation when the sample is large. Okay, so now we're going to make another change. Statistic plus or minus the critical value. Okay, well, my critical value is no longer Z star, it's now T star. Okay, so when you're using means, you're a T star and not a Z star. You also can't use your regular standard deviation of your statistic. You have to replace sigma with S sub x. So inferences for proportion uses Z star, so it's going to be P hat plus or minus Z star times the square root of P hat Q hat. Again, remember that is sample information. That's why they have hats on them. So we adjusted for that over N. And then for means, it's X bar plus or minus T star, and then times the standard deviation. But again, this is from the sample. So we had to replace sigma with S sub x. So both of the standard deviations had to get adjusted because we're using sample information. Normally it's PQ over N, and normally it's the square root of sigma over N. Oh, sorry. It's sigma over the square root of N. But because we're sample data, we have to put hats on our P's and Q's, and we have to swap out an S sub x instead of sigma. So I hope it makes sense. It's not something that you just have to memorize. All right. Check your understanding. Find the critical T star, just like Z star, but this is a T star that you would use for a confidence interval for a population mean with the following setting. So again, we're trying to remember means is T star. Proportions are Z stars. All right. I want a 96% confidence interval based on a random sample of 22 observations. All right, 96 confidence interval for proportions. Okay, so I'm going to draw my t-distribution with a little bit thicker tails. I want 96%, which means 4% left over, so 2% to the left. So normally this is where I would inverse norm. But I'm not a normal distribution, I'm a t-distribution. So we are going to inverse t 0.02 because that is my percent to the left. And then what comes in next is my degrees of freedom. Now remember, degrees of freedom was sample size minus 1, so 22 minus 1 is 21. So I'm going to inverse t 0.02 21. And I'll show you where to get that on your calculator. Okay, but just to talk through it one more time. Normally, this is where I would inverse norm, but I am not a normal distribution. I'm a t-distribution. So I'm going to inverse t. I want to be 96%. That leaves 4% outside, so 2% to the left. So 0.02, comma, degrees of freedom. Degrees of freedom is sample size minus 1, and that's why it's a 21. So then I grab my handy-dandy calculator, and I go to my distribution, and you guys can see number 4 is inverse t. Now while we're here, look at number 6. There's a TCDF. And number 5 is a TPDF. So you've got your normals on 1, 2, and 3, and then you've got your t distributions for 4, 5, and 6. Okay, so I'm going to go down to number 4. So inverse t. Area to the left is 0.02, and degrees of freedom was 21. Oh, I did 211. Let's try that again. 4. Let's take one of these ones out. There we go. Okay. So, and I knew this would give me the negative one because I know that because I did 2%, I'm going to be to the left. So my T star is negative 2.189. T star plus or minus 2.189. So now I'm going to look at number 2. All right, number 2 wants a 99% confidence interval. So that's going to leave 1%, which is 0.5% to the left. So I'm going to inverse t, and I'm going to be real careful, 0.005. Degrees of freedom, come over here to the side, write the formula. 71 minus 1 would be 70. Now that's a very high degree of freedom. That's a lot of observation. So this one is going to look more normal than one with a sample size of only 22. So then I'm going to go to my calculator and my distribution and down to number 4 and 0.005 and were we 70? Yes, 70 degrees of freedom. Boom. Plus or minus 2.648. T star equals plus or minus 2.648. So now you've learned how to find your T star, just like for proportions, you found your Z star. All right, conditions. As with proportions, you should check some important conditions before constructing a confidence interval for a population mean. You still need to be random. Independent, you still need to do the 10% condition, the ln less than or equal to 1/10 of big N, and you still need to be normal. Now I know for this one we are a t-distribution, not a normal distribution. CLT can still swoop in here and save the day. We are still going to call this condition normal. We are not going to call it a t-distribution. We are still going to talk about it in terms of being normalcy. So normal, it's either a large sample, which means the CLT will work, or it tells me that the population is normal. If the population distribution has an unknown shape and your sample size is less than 30, if they give you actual pieces of data, like the original raw data, you're going to type this data into your calculator and graph it. You're going to graph it using a box and whisker. And you're going to look at that box and whisker and you are going to say, it is normal because it has no strong skewness or outliers. And you're going to write both of those things. strong skewness or outliers. So you're going to say normal graph shows no strong skewness or outliers. The following box and whisker plots are from 3 different samples, each with a sample size of 20. So CLT does not swoop in and save the day. If we do not know the shape of the population, could we do a t-distribution to form our confidence interval? Well, I'm looking at the first one, and the first one's a no, because that is skewed right. The middle one is a yes. That is normally distributed. It shows no strong skewness and no outliers. The third one is a no. It does look roughly symmetrical. However, it has 3 outliers. So the first and third are no's, and the middle one would be okay. Now, guys, that's if your sample size is not big enough for the CLT and it does not tell you that the mothership was normal. You can take the individual pieces of data, plug them into your calculator, look at a box and whisker, and we're going to practice all that and state that it's normal. Okay, can we use it? Determine if we can safely use a T-star critical value to calculate a confidence interval for the population mean in each of the following settings. To estimate the average GPA of students at your schools, you randomly select 50 students from the classes that you take. Figure A is a histogram of their GPAs. So first of all, I don't like that it says randomly selected, but I only randomly selected 50 students from my classes. So this was not a random sample. So no. Let's look at the histogram. Yeah, the histogram for part A. Okay, so yeah, that's roughly symmetrical. Like, I'll give you, that's not bad. He's okay, and I don't see any drastic outliers. So this guy is roughly normal. However, that was not a random sample, so no. How much force does it take to pull wood apart? Figure B shows a stem plot of the force in pounds required to pull apart a random sample of only 20, so CLT does not save the day. And I'll look at this, and no. That would be skewed left. So no. Strong skewness. So no. C, suppose you want to estimate the mean SAT math score at a large high school. Figure C is a box plot of the SAT math scores for a random sample of only 20 students, so CLT does not apply. And I know that that looks slightly right skewed, but it has to be strongly skewed. So this would pass. This would pass. It has to show strong skewness or outliers for it to be a no. This is strong skewness. Little AP exam tip down here at the bottom. If a question asks you to calculate a confidence interval, all the conditions should be met. However, you are still required to state the condition and show evidence that they are met. So if you're doing a full-on FRQ, all your conditions are going to be met. Where you're going to get ones where the conditions aren't going to be met is in a multiple choice question. All right. So now we dive in. So we have 2 full FRQs here. We've got one on auto pollution, and the next one is on video screen tension. And we're going to do these things from start to finish, okay? Environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides or NOx. Researchers collected data on the NOx levels in grams per mile for a random sample of 40 light-duty engines of the same type. The mean NOx reading was 1.2675 and the standard deviation was 0.3332. Part A, construct and interpret a 95% confidence interval for the mean amount of NOx emitted by all light-duty engines of this type. So I have sample information. It's asking me to find mothership information. And Part B, the EPA sets a limit of 1 gram per mile for average NOx emissions. Are you convinced that this type of engine violates the EPA limit? So it looks like I'm going to be getting a confidence interval, and I'm looking to see if 1 gram per mile is in that interval. Okay, so here we go. The first thing I'm going to do is define my parameter. Parameter is either mu or p. This is not proportions, this is a mean. So I'm going to start with mu. Now, your parameter is just that. It is a parameter. It is mothership information. So mu, here's how we're going to write it. It is the true mean. Okay, now what are we measuring? We're measuring the NOx emission. True mean NOx emission level. How's that? The true mean NOx emission level of all vehicles of this type. Because aren't they a specific type? Light duty engines, yes. And I don't think it should be vehicles. I think it should be engines. Yeah. Because we're just measuring off of engines. We don't know if these engines are actually in vehicles or not. This could be before they ever go into the frame of a car. Okay, so mu is the true mean NOx emission level of all engines of this type. And here are the two important words. True and all. That's what helps it imply mothership. Population. Okay? So there was step number 1. Step number 2 are my conditions. And I'm even going to label them. Hey, these are my conditions. Now there are 3 conditions. I must be random, I must be independent, and I must be normal. So random. Now they must all be true. So I'm going to go and put my check mark, but now I got to go figure out why. Why am I random? Well, this is a sample. Yep, random sample. Random sample. So I'm going to come back down here and I'm going to go in quotes, random sample. Independent. Well, I know it's going to be true, but so I'm going to go put a check mark. Now I'm going to go find it. So independent comes from the 10% condition, which I must write. And then I'm going to write my formula. And then I'm going to put in my data. Now I think our sample size was 40. 1/10 of what? Of all engines of this type. Now notice, my N does not have anything to do with NOx emission levels. That's X bar and mu. N is just what? What am I getting these measurements from? I'm getting them from these engines. So those are my subjects. Okay, now I need to be normal. Check. I had a sample size of 40. So CLT applies. And let me say why. 40 is greater than or equal to 30. So number 1, yes, I'm normal. Number 2, here's why. And number 3, that's why the CLT applies. So all 3 things are needed. So there are my conditions. I've stated my parameter and I have stated my conditions. All right. And again, and I've said this a couple times, this is kind of where I've noticed that some students get stuck and they don't know what to do next. So focus on what I'm supposed to be doing. I'm supposed to be making a confidence interval. Oh yeah, well there's something on my formula sheet about confidence intervals. Literally says confidence intervals. And it says statistic plus or minus critical value times the standard deviation of statistic. So I'm going to start there. So there's words. Now I'm going to put symbols in here that are relevant to this problem. So statistic could be p hat or x bar. Well, this is means, so it's going to be x bar. Critical value could be z star or could be t star, but since these are means, this is t star. Standard deviation. Well, I need to think about the standard deviation of means. Well, that is normally sigma over the square root of n. However, I don't have sigma. I don't know mothership information. So I have to use sample information. So that's why he switches to S sub x. So I'm trying to help you think through it so that it makes sense, so you're not having to memorize. Okay, now let's put some numbers in here. Well, I know that my X bar was a 1.2675. They gave me 4 decimal places. I'm going to use 4 decimal places. T star, okay, well, I don't have him, so let me shoot off here to the side and let me go find my T star. Now notice when I drew my curve, I drew it with thicker tails. And let's see, I want to be how confident? 95%. So I'm going to inverse T. 5%, cut it in half would be 2.5%. So 0.025. Now I need degrees of freedom. Well, I know that my sample size was 40, so I know my degrees of freedom is 39. However, you cannot just put a 39 in there. You have to communicate to them that you know where this came from. So df equals n minus 1. 40 minus 1 is 39. Then you're going to go type the inverse t, 0.025 and 39 in on your calculator, and you're going to get plus or minus 2.0227. Okay, now I'll say this again because some of you are still messing this up on your test. You have to be accurate to 3 decimal places. I beg of you, do not count a decimal that starts with a 0. So if it starts with a 0, go 4 decimal places, please. Okay, now here's the problem with this. You have this floating number. Do not have floating numbers. He is T star. Label him, anchor him to that T star so that you know what he is. So plus or minus 2.0227. All right, my sigma, which I don't know, my standard deviation 0.3332 over the square root of 40. All right, so I'm going to grab my calculator and I'm going to type him in. And I'm going to start with the subtraction. So here I go. 1.2675 minus 2.0227. Nope. 0.3332 square root 40. Now let me parentheses. There we go. Let me check it. 1.2675, 3332. Okay, I like it. Enter. 1.161. Comma. Then I'm going back, highlighting, scrolling, changing that to a plus sign. 1.374. There we go. There's my interval. I am 95% confident that the interval from that to that captures the true mean NOx emission level of all light-duty engines. Okay, sorry. I got excited. Okay, let's write, it says calculate it and interpret it. So here we go. So I'm going to say that again. This is like your rubber stamp sentence. I'm 95% confident that our interval from that to that captures the true mean level of nitrogen oxides emitted by this type of light-duty engine. I'm going to write it. I am 95% confident that the interval from and technically this has units of measurement. Grams per mile. I'm going to call it the interval from captures the true mean, not proportion, the true mean what? Level of NOx emitted by engines of this type. And you could put light duty engines. I think it says what kind of type it is, but you can put of this type, or you can put of these light duty engines. So there's your rubber stamp sentence. Emitted by, I should have all. Emitted by all. I like the word true. I needed the word all. Again, trying to make sure that I'm communicating to them that this is projecting an estimate for the population, mothership. Okay, it says the EPA sets a limit of 1 gram for average NOx emissions. Are you convinced that this type of engine violates? Heck yeah, because 1.0 isn't even in my interval. It's beneath my interval, like pretty substantially. So if I'm 95% confident that these light duty engines are emitting this much NOx level, and they are only supposed to be hitting a limit of 1.0, then yeah, this is definitely. So you have to state your conclusion, but you also have to state the why, what you're basing your conclusion on. So this is what I wrote. And I'll let you guys write your own sentence. This is what I wrote. Since our interval exceeds the limit of 1.0 grams per mile for average NOx emission, it appears that this type of engine violates EPA limits. One more time, and I know you can pause it and rewind it. Since our interval exceeds the limit of 1.0 gram per mile for the average NOx emission, it appears that this type of engine violates the EPA limit. And I really just got that from the question. Are you convinced that this type of engine violates the EPA limit? So make sure you answer the question by restating the question. Good problem. All right. So this next one, looky there. They are giving me individual pieces of data. You know what I bet that means? I bet that means they don't give me the sample mean or the sample standard deviation. I bet they're going to make us go find it. They also don't tell me the shape, and they only give me a sample of 20. So I don't know if this thing is normal or not. So we got some extra work we got to do in this problem. All right, here we go. A manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh, and too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. Here are the tension readings from a random sample of only 20 screens from a single day's production. Construct and interpret a 90% confidence interval for the mean tension mu of all the screens produced on this day. Okay. Before we grab our calculator, let's do the first step. We can define our parameter, which is mu. And remember, when you write it, you need to communicate to the grader that you know that this is about the population. So mu is the true mean. True mean what? What are we measuring? The true mean tension of all the screens produced on this day. The true mean. When you did proportions, it was the true proportion of all cars in the parking lot, red cars in the parking lot. This is the true mean, and then you have to say what you're measuring. I'm measuring the tension of all the screens produced that day. So true and all. There they are. The next thing I'm going to do, I'm going to roll right into my conditions. Let's see how far we can go without, before we have to grab the calculator. I need to be random. I know it's going to be a check mark. Let's go see why. Where's the talk about my sample? Random sample. There it is. Random sample. I'm communicating to them that I know that it said random sample, and that's why I get to be random. Independent, 10% condition. How many were there? 20? Yeah. 1/10 of all screens produced on this day. I don't know how many that is, but I'm betting it's more than 200. So I assume we're good. Normal. I'm going to go ahead and put my check mark. However, it does not say that the mothership was normal and only have 20 samples. So CLT does not apply. But I have data. So I need to go see the shape of that data. All right, here we go. Grab the calculator. And I need to type my data in. So I'm headed to Stat, Edit, clear out anything that's there. Don't hit delete. And you're going to very carefully type in all 20 pieces of data. Feel free to pause this, get it all typed in. In fact, I'm going to do this on my computer because it's easier. Type carefully. then I'm just going to give it a once over. Oh, see, I already found a mistake. Yep. All right. Okay, I'm all typed in, and I want to see the shape of this. So I'm going to do a box and whisker, so I'm going to quit. And I'm going to go to stat plot, because that's where I can graph things statsy. So I'm going to hit enter. I want to turn him on. And I want a box and whisker, and I want a box and whisker with outliers. So I'm going to that one. Now I have, I was going to say I have an L1, L3, but when you switch to box and whisker, it knows that it's linear or one variable data. So yeah, I want my information to come from my L1. And again, you can choose what kind of little outliers you want. Dots are fine with me. And I'm going to go with the color blue. So I can't just hit graph, because when I hit graph, my window is 10 in either direction, and this data is like in the 200s. So I'm going to go zoom stat. So zoom none. And there he is. And he's cute. He is roughly symmetrical with no outliers. So that is what I'm going to write. So I get to come back here and I get to draw. Okay, here's the thing. So you can't just write roughly symmetrical, no outliers, or no strong skewness, no outliers. You have to communicate to them that you have actually graphed it. So you have to graph him. He does not need to be beautiful. Hold on. It's a little farther to the right. Oh, hello. Okay. There we go. I'm going to put no strong skewness, no outliers. So normal. Okay, so guys, when I grade your FRQs, if you have to graph your data, I'm going to be looking for where you drew it. No strong skewness and no outliers. Concludes, based on this graph, I can assume that we are normal. Okay, oh my goodness, we haven't even done anything yet. We've just stated our parameter and we've done our conditions. All right. So again, this is where I see a lot of people get stuck. So I'm going to remind you, go to your formula sheet for where it says confidence interval, and it will remind you that you are statistic plus or minus your critical value times your standard deviation. Then you're going to put your letters in here. So I'm going to tell you what, pause it and try to put your letters in here. No numbers, just letters. See if you get it right. So my statistic is X bar. Because I'm an X bar, my critical value is T star. And my standard deviation is normally sigma over the square root of n. But because I don't have sigma, I'm going S sub x over the square root of n. Okay, guys, I don't know X bar or T star or my standard deviation. I know nothing. So I need him and him. The only thing I know up here is n. Then separately, I'm going to go find him. So to find what's yellow, I'm going back to my calculator. I'm going to quit out of that. I'm headed to stats. I'm going over to calc. And I'm going to do a one variable stats run on my L1. And make sure your frequency list is empty. is going to give me my x bar and my s sub x. So my x bar is 306.32 and my s sub x is 36.209. So I'm going to come over here to the side and write that down. 306.32, 36.209. Now I can put my x bar in here. Okay, let me go find my t-star. So I'm going to draw thicker tail, so I bring the axis down a little bit. I don't know, what do I want to be, 90%? That leaves 10%, 5% in the wings. So I inverse T because I'm T-star, 0.05 degrees of freedom. How many? I had 20, so 19, but I have to write degrees of freedom is n minus 1, and that's where I got the 19 from. Then I'm going to go back to my sweet little calculator and come on. Nope, try it again. There we go. I'm going to go this distribution and down to number 4. And what are we? 0.05 and a 19. 1.729. T star equals plus or minus 1.729. Very important to have the T star. Very important to have the plus or minus. Like points taken off important. Okay. 1.729. Standard deviation of the statistic is 36.209 over the square root of 20. Now, I'm going to go back to my calculator and type this mug in. I'm going to start with the minus. Tell you what, I want you to pause me. Do this on your own. See if you get the right interval. $292.321 and a 320.319. Okay, now I've completely forgotten what this problem was about. Oh yeah, tension screens. Okay, so pause me. Pause me and write your own sentence. See if you can do it. See how close you can get. Pause me, write your own sentence, and then I'll give you mine. All right, here's what I have. We are 90% confident that the interval from 292.321 to 320.319 millivolts, because that's what they're measured in, captures the true mean tension of all screens produced on this day. One more time. I'm 90% confident that the interval from blank to blank millivolts captures the true mean tension, not the true tension, the true mean tension of all screens produced on this day. Okay, now look, you should be tired. That's a big problem. That's a lot, but always so pretty. It's so pretty, and you did so much. Like you took data, you passed through conditions, you found a confidence interval for mothership information. Like, and you drew your conclusion. Like that's big stuff. My little stats babies are growing up. Y'all are doing such a good job. All right, okay, AP exam tip. It is not enough just to make a graph of your data on your calculator when assessing normality. You must sketch the graph on your paper. It's not enough just to graph it on your calculator. You have to sketch the graph on your paper, and you have to state no strong skewness, no outliers. Okay, again, you are communicating to them. They don't know that you've typed it into your calculator. So you are communicating to them. You can do these on your calculator. You can find a confidence interval for means on your calculator. So if you were going to do the one, the auto pollution one where I gave you the mean and the standard deviation, you're going to go stats, you're going to go over to tests, you're going to go down to T interval. It's going to give you an option between data and stats, and you're going to go over to stats. And then you just enter in your X bar and your S of X and your sample size and your confidence level, and poof, it'll poop out an interval for you. If you're using raw data like the video screen tension problem, you're going to put all your data into L1, and then you're going to do the same thing. You're going to stats, test, T interval, but when it says data or stats, you're going to go over to data, and it's going to pull that information from L1, and it will poop out a confidence interval for you. Now, you will not have time on FRQs to do this on your calculator to check your work, so forget it. The only time that this is really going to come in handy is if you're asked to find a confidence interval on a multiple choice question. But I'm just going to go ahead and say I have very rarely done a confidence interval on a calculator, so that's not really a multiple choice kind of question. If they're going to ask you to find a confidence interval, it's going to be on an FRQ and you're going to find it by hand. Multiple choice questions are going to be like, could you find a confidence interval? Or which variables would you use? Like that kind of thing, more detailed. Okay. All right, and then just like for proportions, we have to be able to choose a correct sample size. So when we did proportions, it was Z star times the square root of PQ over N, and these had hats on them. And if we didn't know P and Q, we defaulted to 0.5 and 0.5, and we wanted that to be less than or equal to the margin of error, and we solved for N. And I said, really focus on the algebra part, being able to type it into your calculator. So I want you to think about how that's going to change for means. The process is the same, but instead of Z stars, we have T stars. And instead of P's and Q's over N's, we have S sub X over N. I'm still solving for N. They're still going to give me the margin of error, and you're still going to do some algebra to figure this out. Okay? We don't know the sample standard deviation because we haven't produced a sample yet. Okay, so let's look at that again. We don't know the sample standard deviation because I don't have a sample size yet. We can't use a T-star because the T-star uses degrees of freedom. Degrees of freedom is little n minus 1, and we don't have little n. So we have two issues here. I don't have a sample because I don't know what little n is, so I can't have a sample standard deviation. I can't T-star because T-star uses degrees of freedom, which is n minus 1, and I don't know who n is. Well, what's the next best thing to a T-star? A Z-star. So we're kicking back to Z-star. Okay, and that's this part. We will also find the critical value Z-star for the confidence level C because we can't use a T-star. It's as close as we can get. It's like the next best thing. It's a good substitute. We will get a reasonable value for the population standard deviation from an earlier or a pilot study. So they're going to say, last year we got this data. Well, that's the standard deviation we're going to use. Or, hey, this other company did it and they got this. Well, we're going to borrow their standard deviation. So we're going to get this. Going to turn it into this. We're going to get this from another study. So it's going to, in your formula, it's going to go back to sigma, and this is going to go back to z star instead of t star and instead of s sub x, because both of these I cannot find if I don't know n. All right, how many monkeys? Researchers would like to estimate the mean cholesterol level of a particular variety of monkey that's often used in laboratory experiments. They would like to their estimate to be within 1 milligram per deciliter of the true value of mu at a 95% confidence level. Okay, so they just gave you that 1. So that's our margin of error. I want to be within that 1 milligram per deciliter. A previous study involving this variety of monkey suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. So there's my sigma. I'm borrowing it from another study. Okay, but I can't just go out and get a crap ton of monkeys. Like, there are lots of issues with testing on animals, so we want to use the smallest amount of monkeys as possible. Obtaining monkeys for research is time-consuming, expensive, and controversial. So what is the minimum number of monkeys the researchers will need to get a satisfactory estimate to be able to claim that we are 95% confident? Okay, so I want to be 95% confident. So I'm going to start, normally I would start with T star, but I can't find T because I don't know N. So I'm going back to Z star. It's the next best thing. Normally I would have S sub x over the square root of N, but I don't have S sub x because I don't have a sample yet. So I'm going to use a sigma from another study. And I want that to be less than or equal to my margin of error. Again, I'm trying to help this make sense so that you're not memorizing. Okay, when I do this, I've got to switch this. And when I do this, it's got to go back to this. I want you to understand it. Okay, so Z star. Well, I want to be 95% confident. Okay, now this is Z star. So I'm now inverse norm 2.5% with a mean of 0 and a standard deviation of 1. That's going to give me a Z star of 1.96. They gave me the sigma from the other study, which was 5. I don't know N. And I want my margin of error to be less than or equal to 1. Okay, so let's talk through what we're going to do algebra-wise here. First things first, I'm going to divide by the 1.96. So then I'm going to have 5 over the square root of n is less than or equal to whatever that number is. And then I'm going to multiply both sides by the square root of n. So then I'm going to have 5 less than or equal to whatever that is, square root of n. So then I need to divide by whatever that is. So that's going to give me the square root of n is greater than or equal to something, and then I need to square both sides. All right, so here I go. I'm going to grab my calculator. And I'm going to start with 1 divided by 1.96. All right, and then that's when I multiply both sides by the square root of n. So now I need to do 5 divided by that answer. Just scoot it back over to the other side. Okay, well that's nice. And that is equal to the square root, well not equal to, it's less than or equal to the square root of n, so to get rid of the square root, I need to square it. So there we go, 96.04. Okay, and then what did we say about decimals for sample size? You always go up, so I need 97 monkeys. All right. So the last thing is interpreting the standard error, and I don't know if it's because this is the last slide of the notes that people just run out of steam, but people really struggle with writing this sentence, interpreting the standard error. All right. A study of commuting times reports the travel times to work of a random sample of 20 employed adults in New York State. Oh my gosh, this is like from chapter 2. The mean is X bar is 31.25 minutes and the standard deviation is 21.88 minutes. What is the standard error of the mean? And interpret this value in context. The standard error, now standard error is different than margin of error. Margin of error is the critical value times the standard deviation of the statistic. That is your margin of error. But the standard error is the same thing as the standard deviation. So my standard error of my statistic is my standard deviation. Again, normally the top has a sigma, but I don't have sigma, I have sample information. So 21.88 over the square root of 20, and that gives you 4.893. So there is my standard error of the statistic. So all you're doing is finding the standard deviation of this mean. So S sub x over the square root of your sample size. Okay, so it's the interpreting where people usually drop the ball. Okay, so listen carefully. I'm going to say this a couple times and then we'll write it. After repeated sampling of size 20, after repeated sampling of size 20, so you have to do it a bunch and they have to all be the same size. The sample mean time will typically vary. Again, remember, we're talking about the standard deviation. Will typically vary by about 4.893 minutes from the population mean time it takes an employed adults to get to work in New York State. So you have to do it a bunch, and it has to be the same sample size, and it's saying that the mean will typically be off, will typically vary by whatever number you got. Okay, so let's write it. After repeated sampling of size 20. So I have to do it a bunch, and they have to all be the same size. The sample mean time will typically vary by about 4.893 minutes from population mean time it takes employed adults to get to work in New York State. Whew. Now, all this is just from the problem. It's that top part, those first 3 lines. After repeated sampling of size 20, rubber stamp it. The sample mean time will typically vary, will typically be off by about whatever you got. Units of measurement, because these are means, not proportions. From the population mean time it takes employed adults to get to work in New York State. I don't know why people struggle with that sentence, but they do. I mean, royally struggle with it. So lock that in. Make sure you're good. All right, so little tweaks, well, maybe more than a little, from 8.2, but that's the difference from proportions to means. So hopefully the more you practice this, the more it'll kind of fit in this nice framework in your brain. But that's where your homework will come into play. So the more you practice, the better you will get.